Hello and welcome to the video on our writing assignment for growth models. So on the calendar you'll see that even though on Saturday I said it would be due then, it's really not going to be due till Sunday, and you get because I'm putting up a new video, I think this might be a little more helpful than the previous one. So to get there, let's go to the growth models writing assignments. We'll click there, and you can select here for the writing assignment. Of course, you know you can always access it by going to the here, and there's the assignments for growth models on this block, and then you can click growth models writing assignment there as well, and you can do some reading about it. We'll get the same thing when we click on the calendar icon for it. So there's growth models, select it here, and it opens it up. It tells us to select two sets of data, two of the data sets from the links below, and here's all these links where you can get data, and I'll show you a few of those. For example, the bald eagle breeding pairs. If you click on that link, it'll take you right to here. If you scroll down, you'll see it has a number of bald eagle pairs here. And then it has data for each of those for the different states. These are pairs of bald eagles in the state. Washington, we have 835 pairs of breeding pairs of eagles. In Oregon, 470. California, 200. It doesn't show Alaska, which has a lot. Florida has 1,166. And then Alabama has 100. And by the way, this was in 2007. It doesn't tell you that. You have to read that to see that. And then this is the breeding eagles in Alabama. And you can see this looks kind of like an exponential growth. Here's the breeding eagles in Arizona. That kind of somewhere linear, exponential in between those. I'd say it's probably more linear just by looking at it. Here's breeding pairs in Arkansas that might look a little more maybe exponential. That's kind of linear, but rather than just look at the data, we are going to, here's another one, the Florida population. This definitely looks exponential if you look at the long term, but if you look just short term, this is pretty linear right here. So if you need a linear model, you could use this starting like 1980. Oh, actually, this one is I'm going to do this one, so you probably won't use this. Yeah, you'll have to do something other than what I've done. So here's one from Florida, 1980 up to 2000. That's very linear. You could use that to do a linear model. If you wanted an exponential, you'd have to go way back here to like 1860 or 1880, and so you get this curve that shows it's exponential. However, it doesn't keep rising up. Usually exponential goes steeper and steeper. So this would not be a great exponential model. It's not terrible, but you would of course have to get this whole curve in for it to be exponential. So the idea of this assignment, though, is that you're gonna find a linear relationship in that data, and then you're going to find another set of data that shows an exponential relationship. So I'm going to give you examples of those two things. Now, if we click on the actual assignment, we'll see here's the links that you can check out: CO2 levels globally, CO2 levels in Mauna Loa, family and hired farm workers in the U.S., melting ice sheets, rising sea levels. All these are topics, and you can pick whatever you want of those. You're going to need two of them. One for linear, that's the first example, has to be a linear equation that you're using and that you find. And so you want your data to be linear. And then another one where you want your data to look like it's exponential, so you have a real curve to it. Okay? And then for question 1, this is the linear one. State which topic you chose that better represents a linear relationship over the selected time period. And then you're going to show the data on in a table, and I'll show you how to do that. We'll find the common differences by using the average difference over a span of time you choose, and we'll compare that to the ratios. So we show that it's a better linear model than an exponential model. So we'll do those side by side in each of the data sets. Then we'll find the actual equation, and then we'll make a prediction. So all these things, all 5 of these things, we're going to do in twice. So if I take a look at this, if I just look at the bald eagles, this would not be a good one for linear. So I'm not going to use this for linear because look how it starts curving up and getting steeper and steeper. That's more exponential. I'll come back to that for part 2. So part 1, I look at the Florida model and I go, well, that kind of looks exponential down here, but I need a linear one. So I'm just going to pick the last few years. And notice that it tells me the actual values. If I go slowly, it has those values right along there. And it tells me, you know, the population in 2000 was 16 million. Then it jumps up to 2010 and we say it's 18.8 million. Then it gives me 2011 and move along. 19.1, 2012, 19.3, 2013, 14, 15, 16, 17, 18. All those values I need to keep track of. So I've already done this, because I don't want to make a long story short. I've already done this and I've gathered that data in this chart. Now remember, here's the 5 things we're doing. We've got a topic. The topic I'm going to use is the population in Florida in just the last 10 years. I'm going to put that in a table. I'm going to find common differences and compare that to the ratios to show that the differences are probably better or as good. And then find the linear model, the equation, and explain what things mean in there, and then make a prediction for a reasonable time in the future based on our model. So let's take a look at this data. So here we go. Like you saw, I put all the data in here. This is population in Florida over the last 10 years. So I started at 2010, and I'm calling that year 0. 2010 is year 0, 2011 is year 1, 2012 is year 2, and so on. So I'm really going to use the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in the population, you can see I filled up all those that came from the table, looking at it, the graph, gave me those values. And then the differences are, now you don't have a difference between 2010 and 2009 here, so I just started with 19.1 minus 18.8. That was a 1 year. From 1 year, I subtract that and I get 0.3. Now that's in millions, so this is 0.3 million. And then 19.3 to 19.1 to 19.3, that's 0.2 million. And then you can see I just subtracted each subsequently. 0.3 to 0.5 is 2, 0.2. 19.5 to 19.8 is 0.3, and then 0.4 and 0.4. And you can see these differences are not constant like we would get in a precise, exact linear relationship. But they're not too bad. It starts out at 0.3, goes down a little bit, comes up to 0.3, goes up a little higher, then comes down and goes back up again. So it's all around 0.3, a little below and a little above. And notice these are all rounded to the nearest tenth of a million. So that was the data, how the data came. So I couldn't get any more precise than that. But as you can see, now these are all the averages going to be around 0.3. How do you find the average over the whole 10-year span? From 2010 to 2020, which is 0 to 10 years, it's a slope. You take the rise, which goes from 18.8 to 21.7, over the run, which goes from 0 to 10. So I got 21.7 minus 18.8, the last value here, minus the first value, 18.8, and it was a 10-year span. From 10 minus 0 is 10. And that comes out to be 2.9 divided by 10, or 0.29 is my common difference. Now I wanted to contrast that with the common ratios, or the ratios, to see that the differences were pretty close. They're all right around 0.29 is pretty close to 0.3, so they vary just by 0.1 millionth or 100,000 in either direction. Now, notice this is the ratios. I got 1.016, 1.010. So this, remember B, which is equal to 1 plus R, really, right? It's 1 plus R. So R is the 0.016 part. It's 1.6%, 1.0%, 1.0%, 1.5. There's 2%, 2%, 1.9, 1.0, 1.4, and 0.9%. So that's a pretty wide variety of the R value or the B value, right? It varies quite a bit. So and the overall average, since it was a 10-year span, by the way, this one, to find B, you take the last value, 21.7, divide it by the first value, and notice it's 10 years, so instead of dividing by 10 like we did on this one, we raise it to the 1/10th power. That is an important fact. You raise it to the 1/10th power. That's how you find the average ratio. Comment, okay? 1.0144, because it was a 10-year span. So I'm not going to use this because I already saw it looked very linear, and these are more consistent than the differences are more consistent than the ratios. So I'm going to use 0.29 as my D value, and remember that's like P sub 0 plus D times N is my linear model. So I let 18.8 be my P sub 0. So notice it says in here, and you should do this, it says let year 2010 be 0, which I did in my data also, and D is 0.29, and the population of Florida in millions. Notice I defined what this P sub N means. I don't just write an equation without telling you what that is. And then N is the number of years since 2010. So it tells you what the N stands for. It tells you what everything stands for. Now, we only use data from 2010 to 2020. That's not a lot of years. And so we don't want to extrapolate too much. That means extrapolate means go beyond the data. But to make a prediction, it is an extrapolation. It means it's going outside of the numbers that we were working with. But I only use 10 years, so I'm only going to go 5 years into the future from 2020, 5 years past what I have. So that means, remember, N is the number of years since 2010. Oops, this is all wrong, because that's supposed to be 15. Yeah, that should be 15. That should be 15, not 25. It's not from the year 2000. So that should be from 18.8 plus 0.29 times 15. That's 23.5. 3.15 rather. And that's our population, 23.15 million in 2025. That's what we would predict the population to be. Yeah, I should have see if year 0 is 2010, then 2025 should be 2025 minus 2010. It's 15 years past the original. So that's our estimate, 23.15 million people. Now, that's the linear, and that's done. That's all we need to do. For number of breeding pairs of eagles in Alabama is what I did what I used the next one, and that was this graph, which looks obviously is really climbing quickly, so that looks exponential. So the data for that, now that is interesting. I better go back to that picture. Notice that this goes every 2 years. I didn't want to put in all those values. You can put in all of them, but I just put in every 4 years. So I started at 1987 because I read this and it said really 1987 is when they kind of started breeding. So 1987, then I went 4 years, 91, then 95, then 99, then 2003, and then finally 2007. So I kind of took a picture. I took a snapshot of that, and I said, okay, in 91, it didn't tell me, like the other one, it didn't tell me exactly what it was. So I said, it looks like that's about 2. Then that looks like it's 5, then 15, then 27, then 45, and then 100. So I just kind of estimated what those were. This might have been 1 or 2. I think it might have been 1, but I put 2 because I couldn't tell in the graph exactly. But that's what we're doing. We're estimating anyway. So that's how I got my numbers 2, 5, 15, 27, 45, and 100 for my table. 1987 was year 0, and then 1991 is 4 years later. 1995, of course, is 8 years, then 12, then 16, and then 20, and there's my values 2, 5, 15, 27, 45, and 100. Now, the differences in this, now I don't want to do differences, but I'm going to compare them. I just want you to see, and I want you to do this too. Show that the difference here, 5 minus 2, that's a difference of 3, but it took 4 years, so you have to divide. It's like a slope. Remember, rise over run. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that's 5 minus 2 over 4 is 0.75 or 3/4 per year. This is 15 minus 5 is 10 over 4, which is about 2.5 per year, and then it goes on from there. I subtracted and divided by 4 every time. Now to find the common ratio, or to find the ratios, you do something similar. You are going to take 5 over 2, you divide like you do the ratios, but this is a 4-year span, so I have to raise it to the 1/4 power. So that's 2.5 to the 1.14, or I put in 0.25 as a decimal. And that equals 1.26. And then we take 15 over 5, right? And that's also a 4-year span from 91 to 95. So we had to take that to the 1/4 power. So every one of these is a 4-year jump. So I did a division, and then I raised it to the 1/4 power to find out what that ratio was. This makes it a 1-year ratio. This is annual then. And lastly, to find the overall, since this was from 1987 to 2007 is 20 years. So for the average difference, I put 100, the rise minus 2, the y, difference in the y's over the difference in the x's is 20 minus 0. So that was a 20-year span. That was an average of 4.9. And this I just wanted to point out that clearly 4.9 being the average, 0.75 is way below 4.9. And 13.75 is way higher than 4.9. So you can see this would not have been a good linear model because there's not a consistency among the differences. On the other hand, on the ratios, it's fairly consistent. This is 1.26, 1.32. That's off a little bit, 1.16, 1.14, 1.22. And then the overall average ratio is you take, instead of 100 minus 2, you take 100 divided by 2, and it's a 20-year span, so you do it to the 1/20 power. And that gives me 1.22, which interestingly enough was that was the same as this last change right here, is 1.22. So I'm going to use B. This is what I'm going to use, a common ratio, because I'm using exponential. And then let's look what we're going to. To find an exponential equation, we let year 1987 be 0, and B, the common ratio, is 1.22. P sub n is the number of breeding pairs in Alabama, starting with 2 in 1987, and n is the number of years since 1987. So the exponential model is going to be 2 the p sub 0, b 1.22 to the n power, the number of years since 1987. So it says we only use data from 1987 to 2007. That's a 20-year span, so we don't want to extrapolate too much. So let's only predict the population in 2020. Now that is like 13 years more, and we only did 20 years. So that's quite a jump, really. And that means n, if we're going from 20, I actually used the population 2015, not 2020, because 2020 was too far. So I only went to 2015 for the prediction, and that difference is 28. So that's that means n is 28 here. So we get p sub 28 is equal to 2 times 1.22 to the 28th power. As you can see, we're using our model to make a prediction for 28 years after the beginning time, after 1987. So that's 523.7, whatever. And it said we would predict there'd be about 520 breeding pairs of bald eagles in Alabama. Notice I wrote, if the growth rate continued at about 22% per year, because that's what we're using, 1.22, remember B is 1 plus R, and R's are 22%. So this may not be likely depending on the habitat. So we don't really know. It would be worthwhile to go and look up and see how many bald eagle pairs were there in 2015, if they were keeping track, which I suppose they would be. I didn't go and do that, but you could, and just to see how good our prediction was. Okay, that's all for now. I hope this is very helpful. Remember, you'll have two questions to answer. One is the linear. Make sure it looks linear and you find the common differences. And two is exponential. Make sure that it's growing exponential and curves up and gets steeper, and that you've got a common ratio and you show that data and compare that to what it would be in the differences, as I have demonstrated here. Okay, good luck to you, and let me know if you have any questions.